We're going to start now. So I will be continuing to talk about group homomorphisms, group theory. Oh, I need a pen. Oh. So lesson 3. And I'll just title this lecture about group homomorphisms, but we'll also be talking about subgroups and properties of these homomorphisms. Right. And before I got into that, so one important topic that will come up is cosets that have to do with subgroups, and we talked about subgroups last time. So just a reminder, a subgroup of a group so say we have a group G, some set with this binary operation, and we have a subset of it. So what makes it a subgroup? So it's a subset first. Inside of the group, so some smaller collection of elements where it's closed under the operation, and it also forms a group under the same operation as in the bigger group in G. So one, it has to be closed under this multiplication in G. Again, meaning that if I take any two elements in H and I multiply them using this product in G, then the result is also in H. So it's closed under the operation. The second was that it contains the identity, and then it also contains the inverses. So H has to contain, I'll call it EG, whatever this identity element is. It needs to be in the subset, and it also needs to have inverses. So if G is in the group, then the inverse is also in the group. Okay, so if these are satisfied, these three, it's closed under the operation, contains the identity, and then if it's closed under inverses, meaning that the first two make it a submonoid, and then the third makes it a subgroup, that it actually contains all the inverse elements. Then we call it a subgroup, and we can we can create a certain structure from, if we fix a particular subgroup H, we can talk about the left cosets or right cosets of a particular subgroup, and this becomes an important notion for counting the number of elements in a finite group or subgroup, and other things as well. Right, so what is a left coset? We'll just do left cosets. Right cosets is a similar notion. All right, so if I fix a particular subgroup H, I'll just write this here. And I think I said this last time, but the notation that we'll use for subgroup a lot of the time is this less than or equal to sign. So H is a subgroup of G. Let's fix some subgroup. Then there's a notion of a coset, a left coset of H. So we'll define that. And usually it's written like AH for some A. Right, so this is called a left coset. And the definition is we're going to take every element in the subgroup H, and we're just going to multiply it on the left by A, and this gives you some collection of elements. It's not usually a group, unless A is the identity. But we call it this left coset notion. So AH, and this is defined as, we're just going to multiply every element in H by A. Right, A is just fixed. So we fix some element in the group A, and then we look at all the left translates of the subgroup H, or in other words, we take every element in H and we multiply it on the left by A. We take the total collection of all these elements, and that's what this set is, AH. This is called a left coset. Right. And so if H has a particularly nice property, which we call normal, then these cosets actually form a group in themselves. But if it's not normal, then they don't form a group. So basically, we need H to have this. If H has this extra notion of normal, which we'll write down in a second what that means, then these actually form a group in themselves, all of these left cosets for every A. But yeah, otherwise it's not. So let me just make another quick statement about finite groups and the sizes. So one thing that's interesting about these cosets is that either AH is equal to some other AH. Like if we vary A, like if we pick one A and one B and we look at AH and BH, then they're actually equal to each other only if and only if there's a certain property of A B inverse. So A B inverse actually has to be inside of H for that to be true. But actually, let me go over something to do with the sizes of these cosets. Right, so there's two important properties for these cosets. So if I fix a particular H again, and I look at all of the different cosets, then they have a nice property, which is that they're all disjoint and they all have the same size or cardinality. So two nice properties is that AH is either equal to BH always, or they're disjoint completely. Equals the empty set. So yeah, this is just basically what I just said. So either the cosets are exactly the same, or they're completely disjoint. They have no overlapping members, so their intersection is empty. And why is this true? I don't want to prove this right now, but another important statement is about the sizes of these elements, or the sizes of these cosets. So the other important statement is that they're always equal in size. So not only are they all disjoint, but if you take their union, you actually get the whole group. So they sort of partition the group into these disjoint subsets, which are all the cosets, and they all have equal size. So let me write that down here. So AH the size of this coset AH is always equal to the size of any other coset BH. And this is just some fixed number. If they're finite groups, then this number, or the size of the coset, is just equal to the size of H itself. So all of the cosets have the same size, and they're all equal to whatever the size of H is, because this is one of the cosets in particular. It's the identity element times H gives you this left coset, which is just H. So these two important statements, just to reiterate what this is saying, all of the cosets are they're either equal to each other or they're disjoint. So AH equals BH is true, or they just don't contain any elements in common. And the second statement is that all of the cosets have the same size, that H is one of the cosets, and if I look at any other coset BH or any other coset AH, then they have the same size, or the same number of elements if it's finite. Yeah, and if the group is a finite group, then every subgroup is also finite because it's a subset. And so for a finite group, the number of cosets, which we usually write this way, G mod H is the set of all left cosets of H. The size of this is actually the size of the group divided by the size of the subgroup. And that's actually why we usually use this notation for left cosets, because of this property for finite groups, that you get this division of the sizes. Right. So let's try to prove some of these statements. I might skip over a couple things, like let's just try to prove that they are actually disjoint if they're not equal to each other, and that the sizes are the same. Actually, just for time's sake, I think I'm just going to prove the one part about the size of the cardinalities being the same. So what we're trying to prove is if we have two different cosets, why do they have the same size? So let G1H and G2H just be two arbitrary cosets. Right, so if I pick two cosets of H, G1H and G2H, we want to show that their cardinalities are the same size. And to do that, I mean, by definition, that means there's a bijection between the two sets. That's, of course, by definition, 1-to-1 and onto. So I'm just going to explicitly define what that map is. So we're going to define a map, call it psi, which takes every element of G1H and sends it to G2H. And the map is, I'm going to send GH to left multiplication by G2 inverse G1. Or wait, actually, other way around. This will be going to G inverse, or actually I'll call the other G, oh wait, no, yeah, this is just G2. So this is G1 inverse G2. Okay. So every element in this coset G1H gets sent to left multiplication by G2 G1 inverse on the left. And so that cancels this G1 here, right? And this is really just equivalent to sending it to G2H. G2 little h. Right, so we want to show that this is a bijection, that it's 1-to-1 and onto. But basically the map is just left multiplication by this G2, G1 inverse. And we just have to show that this is a bijection. Right, but this is actually similar to the proof for Cayley's theorem, because in Cayley's theorem, the map that we're sending it to, like the image in Cayley's theorem, is you have these you have this left multiplication by an element of G, and we said that that map was always injective, and this is going to be injective for a similar reason. So to prove 1-to-1, right, we need to take two elements from the first coset, send them through the map, and see that they get sent to, if they're different elements, they get sent to different elements. So if I pick two elements in G, let's say x1 and x2 in little g1h, so two elements in the domain, if they're not equal to each other, then that should imply that their image under the map, they're not equal to each other. So we want to show that if x1 does not equal x2, then that implies that this left multiplication by G1 inverse, or it was, left multiplication by G2, G1 inverse right, so this is what we want to show, that if we pick two elements in G1H and then we map them using that psi map, right, this is application of psi was multiplying by this element on the left. So if I do that to x1 and x2, we have to show that they're not equal. But if x1 doesn't equal x2, well, that means I'm picking G1H. The H can't be the same that I'm picking for these two elements. So it must be the case that there's some H1 and H2 where x1 is equal to G1H1 and x2 is equal to G1H2. And it must be the case that H1 doesn't equal H2, or else x1 would be the same element as x2. So we have two different elements, h1 and h2 here, assuming that x1 is not equal to x2, and then we want to show that this result is not equal to each other, right? But this result, if I multiply on the left by this G1 inverse, or G2 G1 inverse, the G1s cancel, I just get, So we want to multiply on the left by this thing. So if x1 is equal to this, then that implies when I multiply on the left by this G2 G1 inverse, I get so the G1s cancel, I get G2 H1 and if I do the same thing over here, I get G2 H2. And by left cancellation, we would get that H1 equals H2, but we assumed that they were different, and that would be a contradiction. So here, this is the first part. And then if I do the same thing for x2, I get G2 H2. Right, so we get that, so G2H1, we have G2H1 for the first result, and we have G2H2 for the second result, but we assumed, for the sake of argument, that x1 wasn't equal to x2, so we know that h1 is not equal to h2, and therefore we know that these two elements are not the same. Because we would be able to we can use left cancellation, cancel the G2, and we get that H1 would have to be equal to H2 if these two were equal, but we assume that H1 and H2 are not equal. So that means that when we send this through the map, these two things that we get are not equal to each other, because if they were, then X1 would have to be equal to X2, but we assumed it wasn't. Okay. So that shows a little bit messy here because the board's a little bit small. But just to summarize again, we assumed that we had two elements that were not equal to each other in the domain of this function that we're trying to show is 1-to-1 in G1H. And in order for those to not be equal to each other, that means that there's a G1H1 for the first element that represents it, and a G1H2 for the second one, and H1 and H2 are not equal to each other, or else they would be the same element. And then we basically derived a contradiction because we got to this step and we said, oh, well, that means that H1 would have to be equal to H2, but we assumed that they weren't, so we get a contradiction. That shows that it's 1-to-1. And then onto is pretty easy. So for onto, we just need to pick, let me write down this function again. So we have this function from GH, or G1H, mapping to G2H, two different cosets. And we want to show that the map is onto, so if I pick any element from this coset, I should be able to find an element here that maps to it, and that's exactly what we'll do. So this is to show onto. And so if I pick an element in here, so if G2H is an element of G2 big H, then we just need to find something in G1H that maps to it, but that's not too hard. So if G2H is in here, then we can always find, what is it? It should be the same type of element as the last proof. So if I multiply on the left by G2 inverse and then multiply on the left again by oh no, I did that. Oh yeah, sorry, I need to cancel G1 first and then multiply by G2. So G1 G1 inverse G2, nope. I'm doing this completely wrong. Let me erase this. Right, so we're picking an element in here, and we just need to find what is the element X in here, G1H, such that when I map it through the function psi, I get exactly G2H. So that will show the onto property because we're picking something in the codomain and we're finding something in the domain that maps to it, and since it's arbitrary here, then something maps to everything. So we just have to find out what is this element X that maps to G2H, and the map again was we multiply on the left by, so whatever the element is, we multiply on the left by G1 inverse first, and then G2 on the left of that. So basically, we're just looking for something X such that G2 G1 inverse X is equal to G2H, right? And now we just have to solve the equation for X basically. And equations in group theory are very easy to solve because everything has inverses and everything's associative. So if we want to cancel something on the left, we can just multiply by the inverse of this. So the inverse of G2 G1 inverse is going to be G1 G2 inverse in that order. And so we just multiply by this element on both sides. G2 inverses cancel, the G1 inverses cancel, we just get x is equal to, and then we get G2. All right. So yeah, just get x equals G1H, which is kind of like what you would expect the answer to be, right? If we have something in G2H, what's the thing that maps to it? Well, it's just G1H. So it's the normal map you would think of. Right, and this just shows you that this map is onto, so no matter what element here I pick, G2H, I can always find G1H that maps to it. Yeah. All right. Homomorphism. Okay, so let me do one. Actually, I didn't even really get to group homomorphisms much, but let me see. We wrote down the definition last time. Let's just use it real quick. And let's go over a couple properties. So, right, if we have two groups, G1 and G2, and we have a set function between the sets, so we have some map phi from G1 to G2, it's a group homomorphism if the multiplication of any element in G1, I map it through phi. It should be the same thing as if I map the individual elements through first and then do the multiplication in G2. So this is the product in G1, and this is the product in G2 after I've mapped them to G2. And if this is true, if these are equal for every A and B in G1, then it's a group homomorphism. Group homomorphism, and has certain properties. So first property is that the kernel of the homomorphism is always a normal subgroup. And I probably won't have enough time to go into the writing down the definition of this, but I'll do that next time. So the kernel is a special type of subgroup, which we call normal. And the image is also, sorry, I'll write down the definition of this, but the kernel is everything that maps to the identity in G2. And that means we're looking at elements in G1. So this is a normal subgroup of G1, call it the kernel. But also there's the image of this map, which is everything that's hit by some element in here. So everything that's an element in here, that's the image of this map. That's also a subgroup, but now it's a subgroup of the second group. So the image is a subgroup of G2. And the kernel is a normal subgroup of G1. Right. And then at the beginning I was saying that if the subgroup is normal, there's a process where we can look at the left cosets of this normal subgroup, and they also form a group. So the third statement, which I'll write in a second, is going to be relating the subgroup, which is the kernel of the first group. It's going to be relating the group that's formed by the left cosets of that normal subgroup and the image subgroup in G2. There's a statement about an isomorphism, so these are somehow the similar structures. And I'll write that down right here. Right, so first statement is kernel is a normal subgroup of G1. The image of the map in G2 is a subgroup of G2. And the last statement relates these subgroups to each other in a certain way, which is the statement that All right, so the last one, the third property of all group homomorphisms is if I look at the left cosets in G1 of this kernel, all of these left cosets form a group, and this group is isomorphic to the image group inside of G2. Yeah. So this is called an isomorphism. Of groups. And I really have to go into more detail to make clear exactly what this statement is saying, but it's in English, it's just saying that if I take the left cosets of this normal subgroup, they also form a group with an operation that's sort of inherited from G1, and we have to go over what that means. But if you define what that means, then you show that this is also a group, the set of left cosets of the kernel. And the image, we just said in the last page that the image was also a group, and the statement is that these groups are isomorphic, so they have the same structure in some sense. They might not be written down exactly the same because this is a set of cosets and this is some subgroup of G2, but there is some map between the two that's bijective and preserves the group operations in both. And so we would say that essentially in terms of group theory, these two groups are essentially the same group, that we're writing down different symbols to represent them, but they're actually just representing the same thing. Okay, and then I just wanted to end with one quick example exercise because I didn't want to get through all this without doing an exercise. And I actually invented this exercise. I didn't take it from the book, but it's pretty simple enough. I think it's illustrative of what I'm talking about today. And the example is we're going to have a group, and we're going to have a group homomorphism. And what it's going to be an example of is we have two groups. So one is S3. We talked about this, I think, a couple lessons ago. This is the group of bijections of a set with 3 elements to itself. There's 6 different bijections, which is 3 factorial. And we're going to define a map here to the group Z mod 2Z, which is just, it only has 2 elements, 0 and 1. And when you add 0 to 0, you get 0. 0 plus 1 is 1. 1 plus 1 is 0. And so this is like your modular arithmetic modular 2. And the map is going to send, I'll just write it explicitly. Basically, it sends the identity to 0 in 0 mod 2. It sends any 3 cycle, there's only 2 of them, also to 0 mod 2. And it sends any transposition, which is a 2 cycle, to 1 mod 2. All right, and this tells you where every element goes. So the identity, which is the identity bijection, that goes to 0. The 3 cycle that swaps 1, 2, and 3, rotates 1, 2, and 3, that goes to 0. The one that swaps 1, 3, and 2, that also goes to 0. And then if we just swap 1 and 2, that's a 2 cycle, it goes to 1. So this explicitly tells you where each permutation goes. I'm going to make the claim without proving it that this is a group homomorphism. So that's the first statement. So you would have to actually show that if you compose the bijections here and you add the elements that they map to, that this actually respects the products, or, well, in one it's a composition product, and here it's addition mod 2. So you have to show that this map actually preserves that product, like we just had before, the statement of, you know, phi A times B equals phi A times phi of B. So first, you should show this is a group homomorphism, but after that, it's pretty clear what the kernel is if you know it is a group homomorphism. So the kernel here explicitly is, well, what maps to 0? Well, the identity maps to 0, and any 3 cycle maps to 0, but these don't map to 0. So the kernel is actually all of the 3 cycles and 0, and we call this subgroup A3. This is the even permutations. And A3, like we said, it has 3 elements, the identity and the 2 3 cycles. 3 elements here. And so the statement before the fundamental theorem of group homomorphisms states that S3 mod this kernel. So S3 is a group with 6 elements. This normal subgroup has 3 elements. And so the number of left cosets we said is the division of the 2. So if I look at the number of left cosets of this in S3, there should be 2 of them. And the statement is that this is isomorphic to the image of this map. And this map is actually surjective because we have something that maps to 0, something that maps to 1. And so the final statement for this example would say, if we package what that fundamental theorem was saying, is that this S3 group, the bijections of things with 3 elements, mod A3. So if we look at the left cosets of this subgroup, which is the kernel, this is actually isomorphic to the image of the map, which is Z2, integers mod 2 with addition. And sometimes it's good to just check that the numbers make sense here. And so for the sizes of the group, S3 is a group of size 6, A3 is a subgroup of size 3, and it is true that 6 divided by 3 gives you 2, which is the size of integers mod 2. We just have 0 and 1. So there's only 2 elements. And so everything checks out because the division makes sense, the sizes of the groups. If, like for instance, if you're calculating things and you get a subgroup, a normal subgroup of another group, but this has size 5 and the whole group has size 13 or something, then you did something wrong because the size of the subgroup always has to divide the size of the full group. And in here, 3 does divide 6, and in that case, we get something of size 2. 6 divided by 3 is 2. Okay, so I think I will just stop here. That's all I had written down for today, but we'll do more exercises next time. Probably we'll get into some of the CELO theorems, and I think, what else? So there's, at the end of Jacobson, right, remember we're following this book, guys. Yeah, so there's CELO theorems at the end. Oh, right, and groups acting on a set. So if we have a set, we can have a group that acts as bijections on that set, or yeah, it sort of permutes the set in some way. And these are very important as well. So we'll probably next time we'll talk about groups acting on a set, so group actions, and possibly get into the CELO theorems, or I might do that the next time. But yeah, all right, I'll wrap it up here, but thanks for watching, and bye.